Hello everyone, my name is Andres. Join me in this short video to learn how to model and run a vibration analysis on a simple 2D shear building in S-Frame. We will be following S-Frame's general workflow for today's exercise, meaning that we will first define our structure's geometry by creating all the different nodes, members, and elements that comprise our 2D frame. Then we will be applying material and section properties to all these newly created elements. We will be defining supporting conditions to our structure, and then we will move on to the loading of the structure, which in this case won't be performed using the conventional tools in the loads window. Instead, we're going to be using the lump the mass tool for this exercise. Once this is defined, we are going to move on to running an analysis, which in this case will be a non-stress vibration analysis, and we will then move on to the post-processing of results. So as you can see, I already have a brand new S-frame model open on my screen, and even though I'm going to be building a 2D frame, I'm currently working in 3D mode, as you can see by this global coordinate system at the center of my screen. So the differences between working in 2D mode and 3D mode are not very big. It's mainly going to be a matter of the default constraints applied in each case. I'm going to be diving a little bit deeper into this one as we progress, but feel free, if you prefer to work in 2D mode, to go to the settings menu, click on model type, and choose the modeling type that you see fit. In this case, I'm just going to close this guy because I will be working in 3D mode. So the first step to define the geometry would be to show some grids on my screen so I can make the modeling process a little easier. So I'll just click on the edit grids menu. I may want to check the display grids option over here, and I will be choosing one of S-Frame's basic grids. So this is a 1 meter spacing grid with 10 lines in the positive direction and 10 lines in the negative direction for both the X and Y directions. So I'm just going to click on OK. I can already see my grids showing on my screen. I can zoom to visible structure extents to see the whole set of grid lines, and I'm going to start by defining some members in our structure. So I'm going to the member definition tool. In this case, I'm going to be defining my first 2 columns in this structure. So I'm simply going to use the one joint method in this case. I want these members to be generated in the positive set direction of the global coordinate system, and I want these columns to be, for my first story, I want them to be 5 meters tall. So once I input the relevant information on the data bar, I can simply click on any grid line intersection like you see over here, and in this case I have just created my first column. I want to create a 2D frame with bays that are 6 meters wide, so I can use this 1 meter grid lines and count 6 spaces, 1, 2, 3, 4, 5, and 6, and I can click on my next grid line intersection. So once my first set of columns are defined, I'm going to be defining the second set of columns for my second and my third stories in this building, which will be 4.2 meters high. So in this case, I'm going to lock my grids just to make the modeling a little easier, and I'm going to repeat the process by simply clicking on the upper joint of my first column, and then do the same at the upper joint of the second set of columns. So with this, I've already created 3 stories in my building, and this is going to be a 4-story building. The last story will be just 3.5 meters high. So I'll just repeat the process one more time, and once we already have all of our columns defined, I can go on and click on the 2 joints method to create my beams. So in this case, it will be as simple as joining these 2 joints, and the order in which I click on the joints, meaning the first joint and the second joint that I click on, will be defining the member's local x-axis. As you can see right here, I just toggled on the display element local axis option from the status bar. So I'm just gonna finish with this 2D frame, and once my geometry has been defined, I can move on to defining my material and section properties. So why don't we start off by defining our section properties. I can right click on the section properties tool, which will bring me to this dialog over here with a currently empty list of sections. And for our exercise, we will be defining a couple of concrete sections. So I can click on the concrete button over here, and I will be taken to the integrated concrete design, or ICD, which is nothing but an instance of S-concrete within S-frame. So the general workflow here, to make things a little bit shorter, is to simply select the section type that we want from the left hand side of the screen. In my case, I'm going to select a rectangular column for starters, and for the sake of simplicity and time, I won't be modifying the dimensions or the reinforcement on these sections, but if you were interested in doing so, you can always click on the section button over here to change the different configurations available, and you can also left click on the reinforcing button over here and change the reinforcing of the section that you select. So in this case, I'm not going to modify anything. I'm just going to change the section name to a column. I'm going to click on add, and this will add the column to the section list. So I'm going to repeat the process for a rectangular beam right now. I'm just going to change the section's name and click on add once again to have this second section added to the list. And as you can see right here, we already have the section properties based on what we defined in the ICD, but these section properties can always be modified manually if you wish to do so. In my case, I won't be doing it, but there's always the possibility to do so. So I can simply click on close in this dialog. I will now see my two newly added sections on my section properties legend, and in this case I might want to change the color over here so I can easily distinguish between these two different sections. S-frame automatically assigned the first section, the column section, to all of the members here, but I can simply click on the beam section in the legend and I can apply the changes to make my horizontal members have the beam section assigned to them. Now that my section properties are defined, I can move on to the material properties. So I'll right click on the material properties tool. This will take me to this dialog that will show me all the default materials that are available in S-frame. And in our case, let's not forget that we are going to be working with lumped masses. So for some of you who might be interested in the calculation of the structure stiffness, this is a value that cannot be directly input in S-frame for the structure itself. Maybe we can input that value for a spring, for example, or a nonlinear spring. But in this case, if I want to simplify my calculations for the structure stiffness, I may want to not take into account the mass that's present in my different sections. So in this case, I'm going to grab the nominal concrete that's available in S-frame. I'm going to modify the force density property to have a 0 value over here, and I'm going to click on add to have this 15th material added to my list. I'm going to change the current color to a white color just to make it easier to distinguish, and I'm going to update the material's name. So this will be nominal concrete, 0 density. I will click on update and I can click on close, and this will be the material that we will be using for the structure. So I can simply rubber band the whole structure, and I have applied the nominal concrete 0 density material to my structure. Maybe white wasn't the best color, but well, it won't bother us moving forward. Next step will be to define the supporting conditions for our structure. So I will be clicking on the support tool over here. I will see the 6 different available degrees of freedom, translation about X, Y, and Z, and rotation about X, Y, and Z. And in my case, I want to define a fixed support for these 2 support joints in my structure. So I'll just keep all these options toggled, and I will be applying the changes to my support joints. And with this, we have finished the definition of the geometry for our model. Now that the geometry is defined, we can move on to the loading of the structure, but let's not forget that we were not going to be using the conventional loading tools. This time we are going to be using lumped masses instead. So I'm going to left click on the lumped mass tool over here, and in my case I will be interested in defining lumped masses in the X direction, and I will be able to input the magnitude of said lumped masses over here. I currently have this set in tons, but if you want to change this, you can always go to the settings menu, click on units, and change the force units for mass to a different value here. I'll just stick with tons, click on OK, and I'll start adding my lumped masses, which will be, let's not forget, the only mass that we will have present in our model. So this helps us simplify the calculation for the stiffness for those who are interested. So I'm just going to input all my different lumped masses over here, and once I'm done inputting the last story's lumped mass, I will now move on to defining the shear building condition that we spoke about earlier. So this could be achieved in different ways in S-frame. We could, for example, slave this joint. Let me just turn this guy on. I could slave joint 9 to joint number 10, so they are both translating at an equal distance when these lumped masses are applied. I could also modify, going back to my section and material properties, I could modify these section properties for these columns and beams to be very rigid and have a very high moment of inertia, for example, or my material properties to, for example, have a very high Young modulus over here. But I think that the easiest way to do this will be to actually define some default constraints that we were speaking about earlier. So in this case, I'm going to go to the settings menu. I'm going to click on default constraints, and I will see that for my 3D model, there is currently no constraint for any of the 6 degrees of freedom. So in my case, I basically only want to check for translation in the x-axis, meaning that my columns will be rigid axially and that my beams will be rigid axially and also in flexure. And this will be applicable to all the free joints in my model to move around like this. So the easiest way to achieve this is to constrain every other degree of freedom that is not the X translation degree of freedom. So I'll do so. I will click on OK. And with this, we should be ready to run our unstressed vibration analysis. So why don't we left click on the analysis button over here and select our unstressed vibration analysis type. I will have certain parameters to define for this type of analysis, but I will only be focusing on the total eigenvalues number over here. So for this model, we have a total of 10 joints, each one of which should be able to move in any of the 6 different degrees of freedom in a 3D model. But let's not forget that I applied fixed supports to these 2 joints over here, and I also constrained the remaining degrees of freedom so I could only have translation in the x-axis. So that would leave us with a total of 8 different joints that will be able to move in the x direction. The unstressed vibration analysis will only be able to look at the half of the total number of degrees of freedom available in this model. So we should be able to input a value of 4 here, but if I leave this value as it is over here, we will have some non-zero matrices for the stress and mass matrices, to be more specific, and this will be issuing a solver diagnostic message that will not allow us to complete the analysis as we like. So in this case, I will be going for a total of 2 eigenvalues so we can conclude our analysis, and I will be clicking on OK. But before I do so, if you are interested in extracting the stiffness and mass matrices for any application that you may like, you will be able to do so for the academic version of S-frame by selecting the solution trail detail option available here. I'm currently not using the academic version of SFrame, but feel free to check our separate video for this procedure. So in this case, I will only be clicking on OK, and I will be asked to save my file. I will do so. I will get a clean solution, and now we can move on to the post-processing of results. When we get clean analysis results in SFrame, we will be brought back to the graphical results window, as we can see right here. And in here, given our analysis type's nature, we will only see a couple of options available, one of which is the mode shape tool that I'm left clicking on right now. And with this tool, we will be able to view all the different mode shapes available for our analysis. In this case, the total number of mode shapes will be equal to the total number of eigenvalues that we define in the analysis type window. And right here, we will be able to see not only our structure's behavior when it is vibrating, but we will also see the structure's period, which is basically the time that will take the structure to complete an oscillation when vibrating. We will also see the mass participation in the 3 different directions and the participation factor as well for the 3 different directions. And this information will of course be available for all the different mode shapes. In this case, mode shape 1 may be the one that we are going to be mostly interested in, but we can also see the behavior for mode shape 2, which is a little bit unsettling for some maybe. But all this information can also be checked in a tabular format using the numerical results window. And in here, then again, we will be able to see for each one of our 2 mode shapes the structure's period, its angular frequency and its frequency, and also the mass percentage and participation factors for each one of the 3 axes. So we wanted to run an additional experiment on a simplified version of this 2D frame, so we decided to build this analog model, which is nothing but a simplified column that is not only equivalent in mass, as we can see. I'm only using lumped masses again, and my material properties show me that for the material that's being used, there's no force density, so we're only using the lumped masses, just like we did in the 2D example. And we also modified the section properties for this column section in order to have a greater moment of inertia and to be able to equate both structures' stiffnesses. And what these produces once we run the unstressed vibration analysis is that we will see for mode shape 1 and 2 not only a very similar behavior as the one that we saw for the 2D frame, as we can see, similar in behavior, but it's also similar in numerical values. So we can see that for mode shape 1, in the simplified version, we have a period of 0.64 seconds, while in the 2D frame version of the model, for mode shape 1, the result is 0.63 seconds. So in this case, once again, we are going to be able to compare not only this information for mode shape 1, but also for mode shape 2. And not only that, but we will be able to check the numerical values and numerical results for all of our different mode shapes defined during our unstressed vibration analysis. So with these 2 analog examples, we wanted to show you not only some of the dynamic analysis applications in SFrame, but also how to achieve the same mass and stiffness for different levels of model complexity in order to analyze a structure's behavior. Thank you for watching. Feel free to watch the remaining videos on this playlist and all the content in our YouTube channel.